Okay, Greg, thank you very much for the introduction and the invitation to be here to speak today. I recognize I now have the unenviable task of sitting between you and a lunch we're already about 45 minutes late for. I can hardly hear myself thinking over the rumbling of my own stomach, so I'll try to keep this within that 30-minute window so we can get ourselves off to lunch. So as Greg mentioned, I'm part of the photonic materials effort within CCMR. I'm not going to talk about what I am doing as part of that effort today. I figured I would leave that to the students and postdocs that I brought with me. I'm just going to use a minute to advertise the posters that they'll be talking about this afternoon. One of the activities in my lab is based on solid-state approaches to quantum optics. The idea is hopefully we can use these systems in quantum information science applications. The poster topics today will be, in brief, one about resonance spectroscopy of new emitters in hexagonal boron nitride. We're working pretty heavily with atomically thin semiconductors and trying to come up with approaches where we can make arrays of deterministically created quantum emitters, hopefully each site hosting an individual electron. And then the third poster that Liang Yu will be telling you about if you visit is systems where we can find photons so they interact strongly with excitons, and we've discovered sort of new regimes of polariton physics where these, let's say, new pseudo-spin degrees of freedom that are associated with atomically thin semiconductors become engaged. So I'm not going to tell you about any of that today. What I am going to tell you about has been catalyzed, though, by my ongoing interest in quantum science, and it actually draws on or takes inspiration from two different threads across the last century or so of physics. The first one I think everybody in the room is familiar with, and that's the development of quantum mechanics. Right across the course of the last 100 years, we've learned that particles are waves and waves are particles. There's some weird features of quantum mechanics, quantum entanglement, that were discovered early on when we started thinking about quantum mechanics. More recent times have seen things like entanglement as a resource, and that's really one of the things that empowers quantum information science. And in the course of understanding these things, all right, we've drawn on ideas and techniques from optics, in particular optical coherence. In a nutshell, optical coherence is just, it's a kit of tools that allow you to figure out how much an electromagnetic field is like itself in a variety of different ways. And ideas of optical coherence, in fact, have infused quantum optics studies since the early days. And what the effort I'm going to tell you about today is trying to turn this arrow around and saying, can we learn anything in classical optics by leveraging all of the advances that people have made during the last 30 or 40 years in quantum information science? Right, so can quantum information science inform classical optics in new and interesting ways? And the reason that you would be motivated to do something like this is perhaps there'll be new optical technologies to emerge from this effort. It's easier to deal with photodiodes and lasers than it is to deal with individual photons and photon counting detectors. The effort is not just done by myself. There's a team that works on this at the Institute of Optics. Joe Eberle, Jim Feenup, and Carlos Stroud are colleagues that have contributed to this in various ways. And then there's been an array of students and postdocs that have also worked on this effort. So this idea, right, is not without precedence. If we look back into the 1980s, I would say we had our first interesting connection between quantum mechanics and optics, and that was done by people like Ilya Yablonowitch, Sajiv John, John Janopoulos, where they recast Maxwell's equation, or the wave equation of electricity and magnetism is a Schrodinger equation. All right, so this connection was really between one particle quantum mechanics and electricity and magnetism. The result of this connection gave birth to photonic crystal technology. Now, photonic crystals certainly haven't swamped the marketplace, but these are elements that are of interest in integrated photonics, right? So there was a useful connection between recognizing E and M could be informed by single particle quantum mechanics, gave birth to photonic crystals and photonic circuits. What hasn't been explored to date is what about multi-particle quantum mechanics? So is there room to discover new things in classical optics by connecting many particle quantum mechanics ideas into electricity and magnetism? So to get started on this, we've heard about entanglement a handful of times today. This is just a very high-level slide. There was lots of nice introduction to it. For me, entanglement is nothing but a scenario where you have two degrees of freedom and you somehow can't pull them apart. So in the context of photons, like we heard earlier, you might have a pair of photons that each have a polarization degree of freedom associated with them. And if I can tell you about the state of the polarization of photon 1 without learning anything about the state of the polarization of photon 2, the state is factorized, they're not entangled. If I can't do that, what I mean by that is by learning about the polarization of photon 1, I also learn about the polarization of photon 2, the state is entangled. It's been popularized by Schrodinger's cat. That's illustrated on the right for those of you who don't like the symbology of quantum mechanics. And many people have thought this to be actually one of the defining features of quantum mechanics, in fact, entanglement. And so part of my message today is not to be contentious, but is to actually say that entanglement is not a defining feature of quantum mechanics in any way. In fact, arises in any physical theory that engages vector spaces and has multiple degrees of freedom. As soon as you have multiple degrees of freedom that you use vector spaces to describe, you naturally have states in that physical system that cannot be pulled apart. All right, and so that's the motivating piece of what I'll tell you about today. And so to get this going, kind of the way I visualize it is we have these different degrees of freedom associated with the electromagnetic field, and we just want to map these into a Hilbert space that we use for quantum mechanics. So we can do this formally. This equation across the first line there, that's taking an electromagnetic field. Maybe looks a little bit unconventional or uncommon, but what we've done there, or what I've done there, is identified the different degrees of freedom that one would associate with the field. It's spin, right? We tend to use spin to describe these systems because polarization, degree of polarization has a kind of a well-defined meaning in optical coherence. There's spatial mode structure that can be associated with electromagnetic field, and there's also this temporal degree of freedom. And the idea is you just want to take your field and describe it in these different basis sets, and the modes that go into making up these bases just essentially describe different complexions of the beam. All right, so this is the most generic way that we can express a classical electromagnetic field. One of the questions that I will address today is making correspondences, right, between the states of these classical electromagnetic fields in quantum mechanics. And to really get going on this experimentally in the lab, it's critical that we are able to, again, measure these different degrees of freedom. Our second speaker talked about the challenges with measuring photonic states, and so for us, it's really important to be able to measure each one of these degrees of freedom if we want to be able to say anything about the correlations between them. So there'll be four main messages today. This is the first message. If you tune off or don't listen to anything else after this point, I at least want you to walk away with this, and that is that correlation between electromagnetic degrees of freedom can lead to apparent lack of coherence within the beam. All right, I think most people who think about optics think about uncertainty in a beam of light or an electromagnetic field has to do with some uncertainty in the source that generates that field, and that is not necessarily the case. People who are tuned into quantum mechanics, if you have pairs of photons and you look at the polarization of one photon of an entangled pair, it will seem to be completely unpolarized. So correlations in the joint space can lead to apparent lack of coherence, all right, in the degree of freedom that you're interested in. Being in the Institute of Optics, I teach introductory wave optics to the students. This is my favorite device to describe interference. Some could say optics is all about interference, everything else is details after that, right? So you can learn quite a bit about optical physics just by considering this device. What I'm showing you here is you have some source that illuminates these two pinholes, and you measure an interferogram on your detector. If I just put polarizers in front of the two pinholes, all of a sudden that interferogram goes away. Now, in class, when I talk about this to the kids, we say always that this visibility or the depth of this modulation is a proxy for spatial coherence, right? How the vibration at location A is correlated with the vibration at location B. When I inserted these two polarizers, I've done nothing to the way the vibrations at these two spatial locations are correlated, right? They're still completely correlated with one another. They're just pointing along different directions. But now the visibility has gone away. So somehow, this is a simple example of where using coherence, in this case visibility as a proxy for coherence, is missing something. This gets back to that main message that correlation between the degrees of freedom, in this case the spatial degree of freedom and the polarization, leads to apparent lack of coherence in my field. All right? If you choose to listen to the rest of the talk, you'll hopefully learn a few more things. All right, and these are the other main messages that I'll describe today. Again, coming back to that measurement thing, and hopefully I'll convince you of some new perspectives in interferometry. This will be important for us to analyze the degrees of freedom of a beam. I'll show that by doing this, all right, there are presented new opportunities for optical technology, and I'll give you just one example where we do some imaging using our new approach to interferometry, and then time permitting, I'll keep my eye on the clock, I'll show you how also this is providing us with new insight into classical optics. All right, so critical for these lab activities is a way to engage the different modes of an electromagnetic beam. For certain degrees of freedom, this is pretty easy. So what I'm illustrating for you here is a mode sorter, and the modes that this sorts are the colors that make up the beam. Everyone knows how you do this. You use a diffraction grating. I shine a pulse of light onto my grating, and it splits up the colors of the beam. All right, so this is a simple example of how we're able to sort the spectral content of our beam. What we'd like to be able to do, and now this is not so easy to do in a kind of universal way, is have a black box where I shine a beam of light into it, and what comes out the different output ports now are not the colors, but the spatial modes that make up that beam. So I imagine my box has a setting, and maybe I set it to Hermite-Gauss. I put some unknown beam into one side of the box, and what comes out are all of the different spatial modes that go into that particular superposition. All right, so this was the first question that we wanted to ask, because this degree of freedom can then become correlated with other degrees of freedom. If I want to measure these high-dimensional optical beams, I better be able to measure its spatial mode content. So our solution to this ends up being universal, which is good. It doesn't get us all the way to having that black box that breaks the beam up, but what it does do is it tells us how much power is in a given set of modes that we've set the dial on the side of our box to. And the way that we've done that is using an interferometer. All right, so I'm going to remind you how a conventional Mach-Zehnder or Michelson interferometer works. All right, and then once you understand how that works, I can tell you how we can use this device to analyze the spatial mode content of a beam. And what will end up happening is you'll take that normal temporal delay line of your Michelson or your Mach-Zehnder, and you'll put in what I'll call a generalized phase operator. This generalized phase operator will be the thing that lets us unlock the spatial mode content of our beam. So here's how the time delay of an interferometer works, right? I have my input temporal waveform. It's composed of a variety of different temporal harmonic functions, each with a given weight, all right? It passes through this delay line. Each color gets a phase delay that's determined by its color and the value of tau that I've set, right? So said another way, right, the temporal delay line is just a unitary transformation. The time harmonic functions are the eigenfunctions of this unitary transformation, and upon propagating through this unitary transformation, these eigenfunctions remain themselves up to a phase shift. Right? It's that phase shift that makes an interferometer work. And so that's the important step forward to using an interferometer to analyze the spatial mode content of a beam. We need to come up with a black box that if I put in a beam, and I'm interested in analyzing it in a given basis set, it can identify each one of those basis functions and attach a basis-dependent phase to the function. Right? So essentially what I want to do is find optical transformations that have a set of eigenfunctions that I'm interested in. Once I've made that identification, when my beam passes through that black box, each one of the eigenfunctions that are present in my input beam will get tagged with a phase that's dependent on the eigenfunctions, that's dependent on each one of these constituent eigenfunctions. This hopefully is not too much of a mess, but it tries to bring those pictures back together in a way that is visual. If you're a visual thinker, the math is down there if you want to try to follow along what's happening. But it's pretty simple now. I have my input come in, all right? My input gets split. An interferometer just homodized my input with a phase-delayed version of itself. My black box is sensitive to a particular set of eigenfunctions. In this case, these could be, for example, the Hermite 1D Hermite-Gauss functions. When they pass through this delay line, each eigenfunction gets an eigenfunction-specific delay. Right? Each one of these gets tagged with a delay that's dependent on the eigenfunction that it is. My beam splitter then brings these two things back together. They fall into my bucket detector. All right? They all interfere amongst themselves. Right? There's no cross interference. Remember, something like a Michelson or a Mach-Zehnder isn't sensitive to these phases. Right? And then what I end up with an interferogram that is just an incoherent superposition of all of these other interferograms. Right here. Fourier analysis on this interferogram tells me how much of each input eigenfunction was present within my input beam. Right? So the question now becomes, how do you do this? Or how would I implement one of these generalized phase delays? The way that we've done it in the lab is a proof of principle is to work with something called the fractional Fourier transform. Doesn't really matter how it works. What's nice about it is we can use spatial light modulators cascaded to implement it. And the takeaway message is the Hermite-Gauss functions are the eigenfunctions of the fractional Fourier transform. So what we've done is we've built essentially a Michelson interferometer, removed the delay line mirror, put in this black box that implements the fractional Fourier transform. And now what I can do is I can use my black box to sort the spatial, or let me be careful, analyze the spatial mode content of the beam that passes through this interferometer. To convince you this is the case, here are different Hermite-Gauss functions. So for example, in this middle column, this is the HG41. What I'm showing you here now are experiment in theory. These are the interferograms that are generated by just sweeping the different orders of the fractional Fourier transform. Fourier analysis of this interferogram reveals which spatial modes are present in the input. All right? So this black box allows us to now analyze the spatial mode content of the beam. And the way that we've done this is just generalized a bit how we conceive an interferometer. So now we're going to use this box. First I'll show you of an opportunity that we have in imaging by using this box. So just a small refresher, right? If you try to form an image of two incoherent point sources, diffraction limits the minimum resolvable feature that you can see in your image. Ultimately, it's related to the point spread function of your microscope, all right? And that point spread function depends on things like the aperture of your lens and the wavelength that you're working with. All right? What we're going to do is take a different slant on this. Instead of making a direct image of our 2 point sources, what we're going to do is we're going to use our black box to demultiplex the image that we receive. Right? So instead of doing something that's spatially resolved, we do a bucket detection, but we analyze it now in the Hermite-Gauss functions. Right? This set of functions happens to be well adapted to the problem of imaging just because sort of this lowest order HG00 function, this Gaussian function, looks very much like the point spread function of a microscope. So here is some experiment and some data. So what we do is we shift the beam coming into our black box. This shifted beam is identical to 2 incoherent point sources. What the right column has for you here is now looking in the interferometer arm that has this fractional Fourier transform, looking at what passes through that as a function of the fractional Fourier transform order. The takeaway message from this is the shifted beam puts structure into this function, and this structure will be revealed when I do my interferogram here. So this is an interferogram now for a shifted input beam. It doesn't look like a normal interferogram because it has many, many Hg functions that conspire to build up the particular image that I'm looking at. And here is how that particular image is distributed along the modal coefficients. The takeaway message of this is how well now am I able to determine the distance between these 2 points. What this plot is showing here, these dashed lines, this is what you would expect to be able to resolve if you were using a microscope or some kind of imaging system to look at these 2 incoherent point sources. So this is the Rayleigh limit. What we find here, by doing this approach to imaging where we use essentially this demultiplexing, right, we're able to localize points to distances that are on the order of a tenth, we would say, of the wavelength. In this particular experiment, it's a tenth of the beam size as the relevant comparison. All right? Now, I do want to say with this that there are a couple disclaimers. Disclaimer 1, of course, is I've been very careful to use the word localization. Localization and resolution are a bit different things here. So we're able to localize 2 points. And the reason is because the problem right now is sort of constrained. We know that there's 2 points and we know that they're incoherent. Extensions of this, though, are in the works where we have much more complicated scenes with differing degrees of coherence between the point sources. And then it turns out to be quite advantageous to have access to these higher modes in trying to determine the distances between all of this constellation of points. All right, so I have just about 5 minutes left, and I'll keep us right on track. So the last thing I want to do is now tell you, so we've talked a little bit about the way that degrees of freedom play a role in the coherence of optical beams. I've told you some about how we've had to develop new approaches to interferometry to analyze beams. I've told you how that interferometry approach is letting us do imaging and localization in new ways. Now I want to bring this all back together and tell you how insights, all right, or ideas from quantum optics or quantum mechanics are informing classical optics in new ways, all right? And so to do that, I want to remind you about complementarity. And so complementarity really is sort of a long story across the history of physics, right? From the early days when people were thinking about light, there was always this tension, is light a particle or is light a wave? Quantum mechanics came along and we sort of put our hands up in the air and said, well, sometimes it's a particle, sometimes it's a wave. That's maybe not the most satisfying answer to the problem. Some of the giants of quantum mechanics struggled with this, and I recapitulate some of their quotes. Bohr's notion of complementarity, it's very hard to maybe distill out exactly what he's meant if you've read some of Niels Bohr's stuff. But the idea is, I think if I tried to capture it, is that there are different experimental configurations that reveal particular features of an object, and it's only the totality of all of these configurations that tell you the true essence of the object. So it's a bit nebulous if it's something that you want to test. And so that bothered people, so naturally it was not surprising that questions started to be asked about, can you quantify what does it mean for something to be a wave or a ray, and how exactly do we do that? And that takes us back to this interferometer we saw early on. In this particular apparatus, is there ways to calculate rayness or particleness and waviness? In first attempts, actually got underway in 1979 with a very famous paper by Wouters and Zurich. And what they did in this paper, I'll just sort of touch the surface of it, is they came up with a definition of particle or ray behavior and a definition of wave behavior. So the definition of particle behavior is just its distinguishability. Essentially, you're asking which path does the light wave take. Our proxy for waviness, as we said earlier, or coherence, is just the visibility in the interferogram, and that's easy to define also. And so what they did in this 1979 paper, and there's been many subsequent papers since then, essentially you put these two elements together, you square them, and you get a relationship that is kind of like a complementarity relationship where you have distinguishability and visibility, and one might think that they trade off against one another, but in fact that's not the case. And so what you realize, or thinking back to how maybe Bohr thought about this problem, is there are sort of two things that are at the essence of complementarity. It's that the way you have a sort of a complete description of the system, all right, and the things that you're using as your descriptors are mutually exclusive. All right, so I'm going to convince you that in this relationship right here, that is not the case. And the way that I can do that is go back to our example where we had our two polarizers. All right, and here it's pretty clear that this is not a complete description of the physical system at hand. Why I say it's not complete is that both distinguishability is zero, visibility is zero here, right? Distinguishability, the irradiance going through the two paths is the same, so I can't distinguish which path. The visibility on my detector is zero, and so these two values don't completely describe the system at hand. So there's something missing there. And I can't quite show you that they're not mutually exclusive, but you'll have to take my word for it that I can change the visibility without changing the distinguishability. All right, so those two parameters are not mutually exclusive. I won't go through the details of this, but it turns out the thing that is missing in this description is entanglement. And there's a well-known entanglement measure, the concurrence. The lab, from building this interferometer, we're sort of well set up to analyze beams of this sort so that we can build things like density matrices to extract things like concurrence from these states. And so what we discover in this particular situation, when the distinguishability is zero and the visibility is zero, the entanglement is measured by the concurrence as 1. So bringing all of these ideas together, there is an inequality, in fact, that exists. And this exists for classical beams. This exists for single photon sources. This exists for all optics. It doesn't distinguish between the two regimes. And what's important here is that I can trade now, or I've kind of completed this complementarity relationship by introducing the concurrence, this measure of entanglement. And these three quantities now trade off against one another. And this is something that we confirmed in the lab via tomography and a variety of interferometer interferometric measurements, and just to convince you that we can, in fact, see this sphere when we do the experiment. And so again, my point of view is that entanglement is not necessarily a quantum physics thing. It's a physics thing, and maybe just how you interpret it changes depending on the realm that you're interested in. So that takes me to just about 25 minutes to recap the messages of the day. I won't read them to you again, but I like to conclude just with one quote from Professor Emil Wolf. He's a faculty person at the University of Rochester for a long time. This is from an old JOSA paper, and kind of, I guess, inspires some of this work a bit. And the idea here is that subjects that often appear to be well understood and perhaps even a little old-fashioned have frequently some surprises in store for us. And here, if maybe you can't catch, that's a wolf and a cat, Schrodinger's cat, and they're kind of playing nice together. So I think there's lots of room, and it's better in Rochester because everyone recognizes the wolf right away. So in any case, that takes me to the end of my story. I appreciate your attention, and I have some time for questions. So thank you.
Thank you. So, questions on that talk?
So you did this very nice spatial mode decomposition. Is there any way to generalize this to, let's say, two sort of orthogonal bases, for example, frequency and spatial mode simultaneously?
Yes, that's a great question. So, in fact, that's one of the ongoing efforts is to do basically like a space-time interferometer. So now in both one interferometer arm, you do the 2D spatial mode analysis, and the other interferometer arm, you just do a normal temporal delay, and then you build up a cube now that describes to you the spatial mode content and the color. And you laugh a little bit, but this is really useful for fibers. If you could take the output of a fiber and put it into this box, it will tell you about the colors of the pulses and when they're arriving.
No, I laugh because that's a lot of data.
Oh, yeah, it's a lot of data. It's big data. Come on, everything's big data. So there's three knobs now. One knob, two of the knobs get set. You scan the other one, click, just like that.
How parallelizable is the arbitrary phase delay in your mode analysis? Can you make a mode spectrometer?
So let me say back how I understood what I think you said. So I'd say what we've made here is something like an FTIR, but our FTIR is determined by whatever degree of freedom we're interested in analyzing. So we have an FTIR that works in the Hermite-Gauss basis. That's a function of the fact that we've used the fractional Fourier transform. If I wanted to work, for example, in the radial basis or the radial degree of freedom in the Laguerre-Gauss basis, then I could do like a fractional Hankel transform, and that would let me do a spectrometer now that looked at the radial degree of freedom of Laguerre-Gauss basis.
Thank you, Nick, for the nice talk. So about the last part of your presentation, you showed that sphere with the distinction of visibility and
complementary
squared adding onto one, right?
Mm-hmm.
So is that an experimental data that you showed, or what was it? And this was done with
So I should take that as a compliment then. Yes, this is an experiment. No, yeah, it was data. That's right.
And so it's a lot of photons in the classical.
This is all normal laser beams. That's right.
It carries over to, to a weak pulse. It can carry over to single photons.
So all of the derivations that we have here, we can use all of the kind of modern formalism of optical coherence theory and get the result, or all of the quantum optics of single photons, and we have the same exact algebraic relationship. So the classical experiments have been done. The quantum experiments are coming online in the next few weeks. Basically bringing single photons from quantum dots into an interferometer, and I mean, I don't suspect there will be any surprises when we do the experiment.
Your optics has to be.
Yeah, exactly right. That's exactly right. That's exactly right.
Yeah.
How do you measure C? You didn't really go into that too much.
Yeah, so it was superficial. I agree. We measure a density matrix. So it turns out the entanglement in this interferometer is path and polarization. Right, so we do tomography in those 2 degrees of freedom. So they're both binary, and we measure a 4x4 density matrix. And from the elements of that density matrix, we can extract the concurrence right out of it, and that's how we get the entanglement. So I can talk to you offline about exactly how we did that.
So in the interest of lunch,
Yeah.
we can take any additional discussion to lunch. And so let's thank all the speakers for the